Hey guys, welcome back. So now that we've seen graphically where the economy is converging and that we know one or two things about growth rates of divisions and multiplications, so let's just go ahead and define formally the steady state with population growth. So just a reminder of what we know. So a system is in steady state if all its state variables are not changing over time. And here, with no population growth, then we have seen that we can define the steady state in terms of k. And it's simply when delta k is equal to 0, when k doesn't change. And this happens when investments, so savings times f of k star, is equal to is equal to depreciation rate times k star, so the total depreciation. Now we know that we can't do the same thing with population growth, because new workers always will in the end increase the stock of capital. But what we can do is do the same exercise but in per capita terms. So let's just do that. So pay attention. This demonstration is very useful. So now let's just go ahead and see what happens to the growth rate of capital per capita. So let's say we are at period t. So we can write it as delta kt over kt. And now we know what happens when we have the growth rate of here a division. What is it? Think a bit. Yes, it's the growth rate of the variable at the numerator minus the growth rate of the variable at the denominator. So it's delta kt minus delta over lt. Okay, so now all we have to do is substitute what we already know. We know what is the growth rate of kt, and we know what is the growth is of kt, and we know what is the growth rate of lt. So here I wrote L equal. It is exactly equal if delta small kt over small kt is exactly 0. Not necessarily for all values, but let's go ahead and use the equal anyway to not overburden ourselves with approximations. So what is the growth rate of capital? Well, it's investment minus depreciation. So it's S f of kt lt minus the depreciation rate times kt. And what is delta lt over lt? Well, we have just postulated that this is just a constant, so it's just n, and I don't even have to put a t here. It's something that's always the case. Okay, so now here's a small trick we're going to use. So let's just multiply by 1 over lt at the numerator and the denominator to put everything in per capita terms. So 1 over lt. 1 over lt and 1 over lt. All right, haven't changed anything. And now what happens? Well, we know that 1 over lt times f kt lt is just small f of small kt and 1 minus delta kt over lt, it's small kt, and 1 over lt kt is small kt. Okay, so now let's just see what we get. So we had that delta kt over kt equals to this. So let's multiply by kt on each side. So we find this goes away, and this is multiplied by KT. So delta KT equals to SF of KT minus delta KT minus KTN, and I can put these terms together. And have this KT at the end. So if you observe well, you can see that this is really similar to what we had before. So before we had delta capital KT was equal to S capital F of KT minus depreciation times KT. And now the only difference is that N has appeared here. So it looks strange. We have more population, or population increases, and it looks like it's decreasing capital growth, but we have to know that it's increasing the growth of the capital stock, but it's decreasing the growth of per capita capital. Basically, if I add more workers, then this reduces the amount of capital per worker I have. Yes, so now what is the steady state in terms of population growth? Then it's simply delta KT equals 0. So then I get that SF of KT equals delta plus N times KT. Right, so population, we can see that population growth rate N has essentially the same effect as depreciation. So it decreases per capita capital per worker. So what is the intuition there? Well, in a way, think about, so imagine I'm a firm manager and I arrive today and I see that I have, say, 10 workers and I would like to have 10 machines per worker. And then, but I only have 8 machines. So what happened? Well, maybe yesterday I had 10 and 2 broke. Or maybe yesterday I only had 8 workers, and now today I have 2 more workers. So you see that either my machine broke or either I just hired 2 new people. It doesn't matter. The effect is always the same. It's that I have fewer units of capital per worker and I need to increase them. So we call this effect the dilution effect. Okay, so now we can guess that graphically it's going to look very similar. It's just that's because, well, first of all, F is the same. It has the same shape as capital F. And here, this is constant and this is constant. So this is what I get. I simply get this steady state, but everything in terms of per capita capital. So I get that the steady state is little k star, and it occurs when savings, investment per capita, so SF of small k equals depreciation per capita, so delta plus N small k. And I know that then I'm going to have my output per capita, Y star, my investment per capita, I star, and the difference between the two is C star, so the consumption per capita. So everything looks quite the same, it's just that we have everything per capita. All right, last thing we need to consider is the new golden rule. So let's go ahead and do that. So just as a reminder, the golden rule is the savings rate that maximizes steady state consumption, but now everything is in per capita terms, so we want to maximize per capita consumption, which actually makes more sense since that's what we care about. So let's go ahead and do that. So the consumption per capita at the steady state is written C star, and it is equal to production per capita, F of K star, minus whatever I need to save, so minus S F of K star. And we have just seen that in per capita terms, in the steady state, savings per capita must equal depreciation plus population growth rate times small k. So let's use this. So it must equal to depreciation plus n times small k. And what I want to do is then maximize this. And again, now I choose K star. So same thing as before. I choose the savings rate, but here the neat trick is that I don't need to care about the savings rate. All I do is I choose K star, and implicitly I choose the savings rate. I'm not going to go over all the steps, but just write the solutions. The solution. So I need that f of f prime of K star. Oh, sorry. Equals delta plus n. So this may seem strange. So what you have to note is since f has decreasing marginal returns, so it means that if f prime of K star needs to be larger, then it means that actually K star needs to be smaller if n is larger. So it looks strange because you would think that, oh, if I have more population, I should have more capital. Yes, but I should have less capital per worker. What does that mean? Well, it means that if I have so many new people always entering the labor market, then it's self-defeating to try and keep a very high amount of capital per worker, because anyways, I always have to equip more people. So the optimal thing to do is actually to invest less than I would invest if I had no population growth. So I didn't show what happens to our toy example, but with f of k equals root kn, but I invite you to check it for yourselves.